Hi, everybody. Good morning. My name is Braden Ganetsky. I am so excited to be giving my first conference talk titled Unit Testing an Expression Template Library in C++20. I have another title slide here with my personal logo. This talk is all about compile time unit testing with the backdrop of a parser combinator library I've been passionately writing for the past 2 years. A little bit about myself before we get started. I'm Canadian. You may eventually hear it in my accent at some point. I have a mechanical engineering degree. I got there actually because I really like twisty puzzles, like Rubik's Cubes and that kind of thing. If you want to talk to me about those, I would love to if you want to break from C++. But I do love C++. I've been working professionally for in C++ for 3 years. And I just joined the C++ committee fairly recently in late 2023. I'm very excited to be involved. Importantly for this talk, though, I love parsing. The first time I ever heard of parser combinators was when I watched this talk right here. Ben Dean and Jason Turner's talk, context for all the things. And it's funny that that's the first time I ever heard of parser combinators, because I know they're a common thing, but I was never exposed to them before. And that was my main takeaway, is that they are magical, they're amazing. And so after seeing this talk, I wanted to implement my own parser combinators, and I failed horribly. And I tried a second time and a third time. That also didn't work. But then I ended up trying a fourth time, and that's the library that I'm working with today. Very exciting. I love parser combinators. It's been a big obsession of mine for a while. Before I get into that, though, I want to mention something about unit testing. There was a talk by Michael Oken a few days ago where he mentions, he's right here, where he mentions something about unit testing where you want to isolate the decisions and break up the responsibilities. So imagine, for example, if you have a function that inside of this function, there are logically 3 steps, but they're very coupled. Each step could potentially have 100 different states to it. If you want to fully test the entire thing, but it's all in one function, you need 1,000,000 tests. If you're able to break them up into separate functions, it's additive instead of multiplicative, you only need 300 tests. And I think that's one of the important things about breaking up your code into its logical components where possible. As Tony Vineyard says, approximately, I think, breaking up calculating from doing. Is that what he says? Separating calculating from doing. Yeah. So I think that's very important. So unit testing in general is very important. This talk is about unit testing at compile time. So for an overview of the talk, I'm going to start by demoing my library. It's called Token. That'll be after my introduction, of course. I'll test this library at compile time in multiple frameworks. I will then show off my own framework that I've been using to test my library. And then I'll show some upcoming C++ features that make my own framework a lot better, hopefully in future versions. I want to actually talk about something that might differ in compile time and runtime. I showed this off last year in my lightning talk at CppNow. So I'm just going to show the setup here. You have a structural type, the most basic possible structural type you can have, just wraps an int. You have also the most basic possible concept you can have. It just evaluates to true. I just need a structural type and a concept. And then I template on that structural type as a non-type template parameter, constrained by that concept, creating a struct called checker. And the only thing this struct does is that it checks whether the passed value into its check function matches the structural type in its non-type template parameter. It should be very simple. So the way I call it is that I use an immediately invoked lambda here. I have the checker of 1, and I call .check on this checker of 1. And at compile time, obviously, the static assert passes, right? Because 1 is equal to 1 the last time I checked. But the problem is that in MSVC, I found a bug where it zeroes out the structural type at runtime. So you end up with .check of 0 being the one that actually passes at runtime. So the takeaway here is that sometimes there are different behaviors at compile time and runtime. There shouldn't be. But the thing is, I claim that my library token is fully capable at compile time, and I want to know the full extents if that is actually true. I need to make sure that it actually gets tested at compile time. So for the goals of this talk, I need to be able to test my features at compile time and at runtime. And I need helpful error messages at runtime. Every test framework does this. I've never heard of a test framework that doesn't have helpful error messages at runtime, so we should be safe. But what I really want is to write the test only once, and it runs at both compile time and at runtime. And then even more, I want helpful error messages from my compile time test cases. So we'll see if we're able to do that, but I'm going to start by demoing my library. And this library is called Token. So it's made of parser combinators. it's expression templates in C++20. All of my types are empty types, so everything is just in the type system. There's no non-static data or non-static functions. And I claim that it's fully capable at compile time. We'll see. And it's able to parse spans of anything, not just spans of char. I'll show that as an example soon. But I'll start off with the basic usage. It looks a lot like any parser combinator library you might have seen before. So mine just has its own little quirks, as they all do. So I'll start off by showing the user-defined literals. There's the any of and all of literals, which each take in a string, and they return different types of parsers. So in this case, we have abc underscore any of, and that'll give an any of parser of A or B or C. It'll match one of those characters, and it'll return a span that has a length of 1. Then on the right side, we have an all of parser. That's 1, 2, 3, and that's basically the literal 1, 2, 3. So it needs to match all of those characters in a row, and it'll eventually return a span of 3 characters. And then in the middle, we have the right shift operator, which is overloaded for a sequence. So we put the 2 parsers together. It matches the first one and then the second one. The parser only succeeds if both of those sub-parsers also succeed. So the way we use this, we call .parse. And I'm going to send in the string b1234. So what should happen from b1234? Well, the b, it gets matched in the any of parser. And then it moves to the all of parser, which matches the 1, 2, 3. And then the remainder is 4. Result here is basically an optional, but it has a little bit extra functionality. The extra functionality it has is that it has a dot remaining function, which actually tells you what's remaining in the input. So when I pass it b1234, the result succeeds. The result equals a tuple of 2 spans, and then the remainder is a 4. Any of and all of the UDLs are actually just syntax sugar for the variable templates, any of and all of, where you take in a variadic pack of something. But I prefer the UDLs. I just think they look nicer. I know some people don't like them. I like them in this case. Along with the sequence operator, I also have the, oh, that's not where I was going with this. I want to show actually that it is capable at compile time. So if I change the auto to const expr auto, then I can also change the asserts to static asserts, and this whole thing works also at compile time. OK, now, along with the sequence operator, I have another combining operator, which is the choice operator, the vertical bar that's overloaded. So in this case, it tries to match the first one. If it does match, it short circuits and returns that actual value. If it doesn't match, it moves to the second one, and then it tries that as well. So if I pass it b1234, then the result ends up being b, a span of 1, and the remainder is 1, 2, 3, 4. If instead I change it to be 1, 2, 3, 4b, it tries the any of parser, it fails, then it tries the all of parser, and it returns 1, 2, 3. So, and the remainder is 4b. So this should be pretty self-explanatory. Interrupt me at any time, though. If you want to know more, it is CppNow. Another operator I have is the plus operator overloaded for 1 or more. So in this case, when I pass it abcbad, it'll end up matching 5 of those characters, and then the 6th one will be remaining. And the output type here is a vector of span of char. My span type is called output. So this will be a vector of span of char where each span has a single character. This isn't that ergonomic. I'll show a way to fix that later. And the remainder, of course, is D. The same works for the star operator. These types of operations, Zach Lane spoke about that in his 2-part talk a few days ago. I highly recommend watching his talk on Boost Parser. So mine has those similar types of operator overloads. So this is the 0 or more. So this will actually succeed and return an empty vector if you give it something that doesn't match at all, whereas 1 or more does not do that. Here I don't have const expr auto or static assert. I would love to, but we don't have persistent memory allocations in the language, and it's returning a vector, so I can't do that. But that's a limitation in the language for now. I'll move back to const expr land and show off the tilde operator. So this is overloaded to be a maybe parser. So this will be maybe any of these characters, A or B or C. So if I try to parse ABC, it matches the A and sticks it into an optional. So this is an optional span of char. That's A. If you give it something that actually doesn't succeed, well, then it'll end up being an engaged result. So the result does have a value, but the value that it holds is a std null opt. So it's an optional of optional, effectively, in this case. If you give it something that doesn't work, then, of course, it gives the std null opt. And this worked, yes?
Is there a reason you chose that rather than optional of empty span?
Because in the general case, that may not work because I can put a maybe on anything. So I thought in general it makes more sense to have the optional type be in the result type, not just giving an empty span. Is that
right? But isn't it an optional span? So you're returning optional null opt instead of optional empty span inside optional.
Yes, that is what I'm doing.
Okay.
I think, I mean, I haven't thought about this fully, but I think in the general case, I may not want an empty whatever, because it may not be a span as the result type. It may be a something. So I think it would, I would rather actually return a null op.
Yes. Okay,
Yeah.
I see what you mean.
Yeah.
Sure.
But I mean, in this case, yeah, it would make
yeah.
sense to have an empty span. Okay, so this is sort of basic usage. There's some more overloaded operators, but they don't matter right now. I'll show off the modifiers. Something that I call a modifier, you can put on the front of any parser with the function call operator. There's another syntax I'll show in a minute, but this join parser, it basically takes any parser that at the bottom of it all, it ends up being a span, and at when it actually is running the parse, it tries to join up those spans together as long as they are contiguous. So here, instead of returning a tuple of 2 spans, this will end up returning a single span. So if I give it b1, 2, 3, 4, this is the same as the first example. The result is just b1, 2, 3 as a single span. And that's how you're able to collapse things back down with this join modifier. Another syntax that I use, not just the function call operator, I also have it on the right side with the % sign. Both of these are valid. These are actually the same identifier, just the 2 operators are overloaded. Depending on how I'm feeling, I use one versus the other. I like chaining them on the right side, so it just depends how I'm feeling. Another modifier is, yes?
Is join shallow or deep?
Deep.
Okay.
It goes all the way down. And if the spans that it ends up looking at are not contiguous, barring empty spans, it doesn't look at those. But if the spans that it's looking at are not all contiguous in order, then it does not pass the parse. Yeah. Another modifier I have is the exactly modifier, which takes a size t in its template parameter. So exactly 3 of any of ABC, well, this will return a std array of 3 spans. And that's the first side of the tuple. The second side of the tuple is another span for the all of parser. Now I'm sticking a join on this because the types do get unruly, but I promise you it does work. You just have to, I guess, take my word on it. But if I give it CBA123, the CBA gets matched in the exactly 3 of any of ABC, and then the 123 is the olive, of course. So another important one is the ignore modifier, which takes whatever the result type is and turns it into void. So it just completely ignores the thing. So it still does parse it still does consume the input, but it just ignores whatever the result is. And it interacts in a special way with the sequence parsers. So with the sequence parsers, this would be a tuple of void and span of char. But because there's a void on one side, you can't have a tuple of void. It just unwraps the tuple and just gives the right side. So in this case, if I give it b, 1, 2, 3, 4, it'll consume the b, and then it'll go on to the 1, 2, 3. It returns a single span that is just 1, 2, 3. I find this ignore thing very useful. I find this ignore modifier very useful in stuff like this. So for example, I have an any of parser. It parses any of the digits 0 through 9. I have a dot parser that parses the literal dot, but ignores it. And then my actual parser is a digit followed by a dot, then a digit, then a dot, then a digit. So you could think of this as like a rudimentary version string as long as you can not go above 1 digit. Or 1 digit per section. So then if I want to parse 1.2.3, even though this is a sequence of 5 subparsers, this will end up giving me a tuple of 3 things. So I find this useful to ignore things. Boost parser and Spirit, they have this idea of a skipper. I don't have skippers in this library. I do it in a more explicit way like this. So I am the only user of this library, hopefully forever. So, I do it how I like it, and I think it's nice. But if you have any criticism, I will happily take that as long as you're faced away from me and walking away. So next modifier, no, I'm just kidding. Next modifier I want to show off, I'll start by, I'll define this function here. I'll call it is1, which basically just checks if the first character is a 1. That's all it does. And the way that I use it is by putting it into my fn modifier, which is basically a mapper. So it takes whatever the output was from the previous parse, from the child parse, and passes it into that function that it's looking at. It's in a template parameter. And it has to be in a template parameter because it's an expression template library with no state in any of its types. So I need the thing to be in a non-type template parameter. And so I take the NEF parser of 0 or 1. When I pass it into this function, the return type ends up being a bool. And then with exactly 3, the return type is a stood array of 3 bools. So when I try to parse 1, 0, 1, 0, anyone want to call out what's going to be the result? Array of true, false,
Array of
true.
false, true, and remainder 0.
And remainder 0, yeah. So I find with these sorts of things, there are other modifiers, of course, but I'm not going to show them off here. With these sorts of things, I can get all the use cases that I'm looking for. So I like doing it this way, yes.
Is it ever inconvenient that capturing lambdas are not structural types?
Not in my experience.
Okay.
Yeah, but I haven't needed that. And I'm sure you could come up with a use case where you would need that, and then it might be very annoying. So yeah. I'm going to show off the non-char spans now. Because this parser library doesn't actually care about chars. It doesn't care if it's parsing chars or parsing ints or parsing really anything. So here I'm going to take a vector of int of random numbers, and I'm going to make 3 parsers. The first one I'll make is an even parser. So it parses any of the ints 0, 2, 4, 6, 8. These are not chars. These are actually ints. And then I have an odd parser which does the same thing. It looks for any of the ints 1, 3, 5, 7, 9. And then my total parser, I'm going to look ahead through all of the even numbers. I'm just going to ignore those. And then I'm going to find a span of as many odd numbers as I can possibly find. So what this will actually output in the end, once I parse it, this will actually output a span of 4 ints that are 5, 1, 3, 1. And then the remainder will be a span of 5 ints, 4, 7, 1, 9, 3. These numbers have no significance. I was just typing. Yeah, I'm comparing them to vector just because that's the easiest way to do the comparison on this slide, but they are actually spans, not vectors. A really important use case for non-char spans, in my experience, is if you're trying to write some sort of parser for tokenized things. So I'll take you through this. If I have an enum called token kind, let's say I'm tokenizing a language, and I break that down into identifiers or numbers or left braces or different operators, all the different possible kinds that I can have in a tokenization. Then I have an actual token class, which knows what kind it is. And of course, it has other members. And the important thing is that it's equality comparable to token kind. And that actually allows me to use it later inside of a parser that at the lowest level has a token kind value type. So I'm going to grab my tokens. Doesn't matter how I grab them. And then I'll start creating some parsers. So I'll create a qualified name parser. And we all know what a qualified name is. It's identifiers delimited by double colons. So the olive parser now has a value type of token kind, as does the inner olive parser inside the delimit modifier. And then that means that entire parser has a value type of token kind. And then whatever, I do some more stuff. And then I say that a function declaration in my language is a qualified name followed by something and something. It doesn't really matter for this demonstration. But the point is that the function declaration parser has a value type of token kind. But I'm trying to parse a span of token, not a span of token kind. And the key here is that token is equality comparable to token kind. So I can actually do this, even though token cannot be a structural type in this case. I guess I forgot a public here, but whatever. Even though token is not a structural type and it cannot be used as the value type of my parsers, I can still actually parse spans of token just fine as long as at the lowest level the value type of the parser is a structural type. So I find this to be quite useful when I'm doing stuff like this. One important part of parser libraries, will be the last part that I talk about, is recursion. And I'm going to show that off with JSON. So here's the json.org webpage. Let me scroll. Oh, look at that. I can't scroll on my screen. There we go. So on json.org, they have these really nice railroad diagrams. And they show off the syntax in a really, I think it's a visually pleasing way. So I'm going to use these, and I'm going to implement a JSON parser. This is also a callback to Ben's talk as well, where he does that kind of thing. I'm not going to show off any of the ones that are not recursive. I don't really care about those for these slides. I'll show off the recursive ones. So back to my screen. an object depends on a value. An array depends on a value, but a value depends on object and array. So it's mutually recursive. How do you do this with expression templates? So the way that I decided that I want to do this with minimal overhead to the user is I create something called custom. It's a CRTP, curiously recurring template pattern, where you have to inherit from a template of yourself. So I have JSON value inherits from custom of JSON value, and you got to give it two things: the result type and the get parser function. I'm forward declaring both of those things. The result type sometimes can be deduced. In this case, I don't think it can be deduced. So I'm forward declaring the result type because it actually depends on the result type of the object in the array. For the object, the result type is, in general, it's a mapping from strings to values. So here I'm representing that as a vector of tuple of string and value. An array is a little bit simpler. It's just a vector of value. And then finally, I can define my JSON value result type, which depends on the result type of the object in the array. It just wraps a variant of those things. As far as I'm aware, if I just made the result type itself a variant, that wouldn't work because it would be an infinitely long, self-recursive type, which I don't think is possible. So I need to wrap it inside of this result type struct. But this all works. It's all the possibilities that can go in a JSON value. It's a string, or a number, or an object, or an array, or a bool, or a null. So I'll go to the get parser function for JSON object. I'm just going to read the railroad diagram, and let's see where we go with this. So the get parser function, I like making it const eval. I mean, it doesn't have to be, but I like making it that way. It does have to be static, though. That is important. I'm just going to create the inner pair. So on right here, this pair, I'm calling it a pair, white space and then a string and then white space and then colon and then a value. So I'm just reading that, and I'm putting that into my library. So it's white space followed by a string and then white space and then colon and then a value, and that's it. But because white space is an ignored parser, and because colon is an ignored parser, the result type actually ends up being a tuple of two things. So that's quite useful. And then in general, an object is not just a single pair. It's a bunch of pairs delimited by commas. So I go through that in the object. And then the total parser is just a left brace followed by either an object or a white space followed by a right brace. That's it. This is the full implementation. Not hand waving. This is actually checked into my repo. Same with JSON array. It ends up being even simpler because JSON array is just a bunch of values delimited by comma. And then the total parser is a brace followed by an array or a white space followed by, a bracket, not a brace. And that's the total parser. And then the parser for JSON value, this actually ends up being a little bit simpler because there's no looping. So I'm just going to read it. It's a string or a number or an object or an array or a true or a false or a null. So I can just read from the railroad diagram directly into my library, and that works. I do need to wrap it into this into modifier because, again, the result type is not itself a variant. It wraps a variant, so I need to put it into what the thing that it actually is. And then the total parser is white space followed by this inner parser followed by white space. And that's it. And it works. So I take this example string from json.org, and if you squint your eyes, you might see that this is the Visual Studio debugger that actually does properly parse this string right here. So that's my library. Now I'm going to test it because I want to make sure that it works. I can tell you that it works all I want, but I need to actually prove it. So I'm going to go through some unit testing frameworks. That'll be the bulk of this presentation. I'm going to go through the frameworks: Google Test, Boost Test, Catch2, Doc Test, Snitch, and UT. And the way I'm going to do this is by first setting up a test case. It has to be the same for each framework. I'm going to do a basic runtime test. I'm going to make some custom error messages at runtime. Then I'll do a basic compile time test, and fingers crossed, I can get custom error messages at compile time. But we'll start with the test setup. So I'm going to make a parser that parses any digit 0 through 9. And then I'll say that a year parser is exactly 4 of these digits, but joined back into a single span. A month is the same, but it's just 2. And then a day is exactly the same as a month, but with different syntax. And this will be important in case I want to test equality of the combinators and make sure that it's actually doing the right thing. The total parser, I'm just going to parse ISO 8601. So pretty simple use case. It'll be a year followed by a hyphen, then a month, and a hyphen, and a day. And there are a bunch of things I can test. I can test the parse result. I can test the combinator operations. I can test parser equality, like month and day. They should be equal, but who knows? And then I can test parser properties. The bottom three of these are strictly compile time in my library, but the parse result is runtime and compile time. So I'll start with Google test, and I'll start with runtime testing. This is a basic Google test. I'm calling it ISO 8601 parse result. And I'm just going to call .parse on my parser for January 1st of this year. So hopefully, if all goes well, then it will pass the assert and the expect here. So this assert true, this is going to be a fatal error, so it's going to fail the test if that doesn't pass. The second one, it can be assert, it can be expect, it doesn't really matter. But the point is, if the first test case fails, then the second test case is trying to dereference a disengaged optional, which is UB, which at compile time isn't going to work, so this is going to be a constant theme throughout this part of the presentation. So yeah, this one's fatal, this one's non-fatal. The second one could be fatal, it doesn't actually matter. So that's the test. And this is the output that I get. Pretty explanatory output, everything works, great. Yes?
Can I just ask, you said you can test parser equality. Are you testing that extrinsically, or did you implement structural equality between?
I'm testing it, I test it extrinsically, but I do have an operator equals in my testing framework for the parsers and the modifiers specifically to make sure that they're equal. I don't actually have them in the library, so you can't like double equals. But yeah, I'm just checking to see that the types are the same because there's no non-static data. Okay. So if the types are the same, then they are the same. Okay. Yeah. If I put in, instead of the string 2024-0101, if I give it the string like bad, for example, BAD, it'll tell me this. It failed. Okay, so result.hasValue failed. But I want a better error message. So what I'm going to do, I'm going to take this test. I'm going to look at this auto result equals parser.parse bad. I'm going to factor out that bad into an input so that I can use it later. And then instead of my assert true just being by itself, I'm going to pipe on a message. And in C++20, because my library is 20, I'm going to use std format. So I'm going to say that the input could not be parsed. I'm going to show what the input is, and then I'll show what the parser is, and it's pretty printed. So hopefully that'll catch any issues here. So then when I go to print this out, it ends up saying that the input couldn't be parsed where the input is bad, and this is a pretty print of the parser right here. And immediately I can see that, well, yeah, there's a problem, because at the lowest level, all of my any of and all of low-level parsers, they parse either digits or hyphens, but I'm trying to parse characters. So yeah, this is like very obvious of what's going wrong here, whereas the message before was not quite as obvious unless I look at the code. So I like giving a good user experience, and in this case, I'm the user, I want the good experience. So here's the test case again. Let's say I try parsing February 29th. This year was a special year. We had a February 29th. I want to make sure that works. And this is just checking syntax. It's not actually checking semantics or anything, right? So there should be no problem with February 29th. But let's say I have a problem in my implementation, and for some reason February 29th fails. But why does it fail? Syntactically, that should work. So I think actually showing the parser, what the parser is in a pretty printed sort of way, this will show what the problem is. And in this case, it looks like, oh, my UDL probably just dropped the last character of the string literal. And this actually will show, like I can take a look at this message and go, oh yeah, I obviously know what the problem is. As opposed to no message, which won't tell me that. So I'm just making the case why custom error messages are important. I'm sure for those in this room, I don't really have to make that case. We all want to have a good user experience. So I'm going to give Google Test a passing grade for runtime testing. It's great. It does a good job, does what it's supposed to do. And there's a few maintainers of Google Test in the room, so doing a good job. Boost Test is another testing library. It's been around for quite a long time. As far as I'm aware, it's since 2001. Can anyone correct me on that? Anyone know? 2001? Yeah, OK. So it's a while. And it does its job well. It has these macros boost require and boost check, which do the fatal and non-fatal assertions. One of the problems that I found, though, is that in require and check, you do these, I think it's called destructuring, is what they call it, where you take the left side of the equal sign and the right side of the equal sign, and you try to make a nicer error message, which would be great if boost test didn't actually require this. So in this case, because tuple is not streamable, I can't actually do that. I'm going to sidestep the problem, though. I'm just going to put parentheses around the whole thing because I don't care. So anyway, it works. The whole thing works. But that's not the interesting part. The interesting part is if I give it something that fails. So if I give it, again, bad, it tells me that result.hasValue has failed. And that's useful. But again, I want the custom error message, so I'll show you how to do that. Instead of boost require, I use boost require message. So right here, I have my same std format. You will see this a million times in my presentation because I want to keep it consistent between frameworks. So now I have boost require message. So once this test case fails, it ends up showing me this output. And then if I have my February 29th case, when I've implemented my UDL badly, then I know exactly what the problem is. So similar to Google test, boost test does get a passing grade. And I'll take a water break. Next up is catch 2. Oh, yes.
Have you considered, in your parser library, if it parses and fails, you have some information about the specific place where it failed?
So at the moment, I don't have any good error messages as to where the parse failed. I just have that the parse failed. Okay. I do feel very inspired watching Zach Lane's 2-part talk a few days ago to actually add this kind of stuff into my library. It seems really cool. And it's something that I've wanted to do, but I haven't had a good mental framework for it. But now I think I do, so I am going to add that sort of thing. But no, it doesn't tell you where. And actually, yeah, that might also be a problem in the error messages. So that is a good point. Next, I'll try catch 2. I'll see how that works at runtime. I'm setting up the test case in a similar way, and it has these same sort of require and check macros. And again, require is fatal, check is non-fatal. In catch 2, it does the destructuring, or whatever they call it, with across the equal sign, but it doesn't require that that happens, so actually everything works. So that's nice. In the bad path, the sad path, it tells me that result.hasValue failed, and when I want a custom error message, in catch 2, I use this info macro, where I pass it some sort of message, and then that's in the scope context. When this info goes out of scope, then that message is no longer on the stack, as far as I understand it. So anything that fails now is going to have this message attached to it. So now when this bad fails, it gives me the message that I'm expecting. And again, in the February 29th case, it gives me the type of thing that will help me diagnose the problem. So I'm giving catch 2 a passing grade for runtime testing. And you'll see this is a theme, that every test framework gets a passing grade for runtime testing. Yes?
Is there only one info message? So if it failed to parse or parsed the wrong thing out, you wouldn't be able to distinguish between those two different failures?
Yeah, in my case, I couldn't distinguish between those two failures, but I'm also only testing the first case because it's slideware. If I was actually doing this, I would put the require inside of another scope, and then I would put one info macro for that, and then the check would be inside of another scope with a different info macro. But yeah, just slideware. You can pretend like I put this info macro with the require, even though I didn't. So yeah, I'll give catch 2 a passing grade here. Next up, doc test. This test may look similar to catch 2, and that's because it uses the same syntax, which is nice because catch 2 is really popular and the syntax is really nice. So I like it. This is what it gives me for a passing test. And then for a failing test, this is what it gives me. And when I want a custom message, you may already guess what the thing is. It's the info macro. So it's exactly the same thing. So it gives me that message. And then in the February 29th case, it gives me this message. And I moved my mouse by accident. And that's a passing grade. Wonderful. Next up is snitch. Snitch has, again, the same exact syntax as catch 2, which is nice. It makes it easy to use. It's a drop-in replacement. Well, for now, at runtime, it's a drop-in replacement. So this is it passing. And then in the bad path, this is it failing. With the message, we understand this song and dance. So here we go. And passing grade. Who would have thought? And then lastly, I'll show off UT. UT is actually very different. It's a macro-free library. So the way that you define a test is by the assignment operator from the _test UDL. And then inside that, I use the expect function. If I want a fatal error, skip ahead some of my highlighting. If I want a fatal error, I need to pipe on stream on the fatal identifier. And that's just inside of that's outside of the expect call. So this ends up sort of doing the right thing, and this is what it gives me when it passes. When it fails, it tells me that a test condition has failed. It doesn't tell me which one. Because it's not a macro, it can't textually take whatever was in the expect. So it's a little bit more, a little bit less helpful here, except for the fact that you can put error messages wherever you want. So I'm streaming it on. You stream it on between the expect and the fatal. So I have this same std format. And then again, in this bad path, it'll give me the message that I've been expecting the entire time. So here's the message. And here's it for my badly implemented February 29th. And that's good. So that's runtime testing. But that's easy, because we all know runtime testing. Let's talk about compile time testing. So for a level 1, I'm going to talk about testing things one at a time. And then if a testing framework is able to run that gauntlet, let's go through the parameterized. The test setup is going to be exactly the same. And I can test, again, these different things, like properties like the value type, or whether p is a parser for this value, or the family. So is it a sequence parser or a join parser, etc. I can test which of the parsers are equal to each other, like month or day. I can test the combinator operations, and I can test the parsing, most importantly. And the parsing is the only thing that is like really vital here, because the other ones are like, you know, they're just kind of traits. But the parsing is not a trait, so that's important. I am going to use some aliases, though. This might make it more helpful. So I'll have everything that's in a capital is going to be the type. So let's look at Google test. With Google test, there's a function called static assert type equal. And you may notice a bug on here. I have int on this line, but the value type is actually char. So I want to see what it gives me. It fails the compile, telling me that t1 and t2 are not the same type. And then also, this is actually helpful as well, in MSVC, which I use, see reference to this function template with char and int as the function, as the template parameters, which is helpful because in my source code, it doesn't say char and int. So that might be helpful to read. But then my question is, how is this different from just a static assert on same as? So, I mean, I have this same bug here, and it gives me a similar static assert message. It just says that char and int aren't the same. And in case that wasn't clear enough, on the second line, it says char and int are different types. So yeah, in C and C++, sometimes char and int aren't different types, I guess, so this might be helpful. Yeah, so it gives me a same message, so I don't actually have to use Google Test's function. And if I want to do some more functionality that's not just checking whether two types are the same, well, that might be a little bit more complicated, but we'll get there. For now, I'm still checking if things are the same. So like month and day, those need to be the same. But if I want to check if year and day are not the same, Google Test doesn't have anything for that. So I do need to use the static assert for the more complicated, putting a bang in front of it. I can also test the combinators to make sure that day and month put together ends up being a sequence of day and month. And like, yeah, this is obvious. I want to test it. I want to make sure that the things I claim in my library are the things that actually happen. And then I'll take my ISO date parser, and I'll parse a bunch of things for it. So first, there are some properties. I want to make sure that it satisfies the parser concept. I want to make sure that the family is a sequence. So just these are different things I'm able to switch on in my implementation. And then I want to make sure that isodate is a parser for span of char. Going even further, I want to make sure that the result for a span of char is a tuple of 3 spans. And that's very important. I want to make sure that the results are the same. Now notice actually, it's result for, it's not just result type. And that's because all of my parsers have a result for alias template, because you can parse anything that's equality comparable to the value type, not just the value type. So you do actually need to check that the value type is, it may be different for different types of inputs. And now let's test the parsing. This is the most important part. I want to make sure that when I try to parse January 1st, it succeeds. I want to make sure that when I parse January 1st, that it's the expected output. And then I want to make sure that when I parse bad, well, it doesn't succeed. So let's take this part and let's factor it out, because this is a lot of repeating myself, and I just don't want to repeat myself. So I'll put it into a macro. And in this macro, it's going to take in the parser, the input, and the expected result. I'm going to do a compile time assertion that the parse succeeds, and then a runtime fatal error if the parse does not succeed. And then I'll do the same thing checking for the result, both at compile time and at runtime, but this time non-fatal at runtime. And there's no such thing as non-fatal at compile time, so it's all static assert. It would be nice if we had static warning, but that's out of the scope of this talk. So now for this test, I can just assert that this parses successfully. So I give it the input, I give it the expected result, and it works. And now with the same setup, let's try to give it bad. So it's going to fail the first static assert, and what it tells me is static assertion failed, expression did not evaluate to a constant. Which, it doesn't tell me which static assert is failing. And you might want to say, well, you can just stringify what the message is, right? Because it's in a macro. You can just put that as a string and then put that as the static assert message. Yeah, but my point is I'm looking for a framework that knows how to do this kind of thing. And also the question here might be, am I actually using Google Test? Right? Because like, yeah, I have my test macro and I have my assert and expect macros, but like, I'm looking for compile time testing, and I'm using static assert raw in C++. So I am very sorry to give it an X. It's a great library. I use it at work. It's amazing for runtime testing. I'm looking for compile time testing. So with boost test, it actually is a similar story for Google test. And actually, it doesn't even have that one function. So it's just static asserts. Yes.
Can I ask you to dig into the error message on the previous slide? Which
Sure.
why, where? Oh, it's inside optional. What did it try? Why did it fail exactly?
So actually, 2 static asserts are failing. Both of them are failing. The first one
not
is
just reporting the first one.
well, I think it's reporting both.
Okay.
The first one's failing. Well, actually, no, sorry. It's not reporting the second static assert because the second static assert has UB at compile time. So it ends up actually being a compilation error before it gets to the static assert. And this will actually be something we see in the other test frameworks that I'll have to guard against this. The first static assert is actually failing. But because that fails, then I have an optional that's disengaged. I'm trying to dereference an optional. But at compile time, there's no UB at compile time. So I can't dereference a disengaged optional. So it's just a compile error.
Sure. I'm just confused by the message, like undefined function or not declared context, where is a strange message for that.
Me too. Yeah, I mean, it's it's basically how MSVC says you're invoking UB at compile time, at least as far as I understand. So with boost test, it's a similar story. These static asserts is really all we have. So I can factor this out into my assert parse success macro. I can run my assert parse success macro here in this test, and this all succeeds. If I try to make it fail in the bad case, this is the same implementation. It gives me exactly the same message that it gave me with Google test, which actually shows my hypothesis that I wasn't even using Google test in the first place. So here I'm not really using boost test, so I'm going to give this an X as well, and I'm sorry for that, because boost test is a very battle-tested library that works very well for what it does. It's just it doesn't do this. Next, I'll look at catch2. Catch2 has something interesting called static require. With static require, you can configure the behavior using this macro catch config runtime static require. You do also need to include extra things as far as I'm aware. But this ends up, if you configure it the way you want, it ends up running your assertion both at compile time and at runtime. So this ends up working. It says 3 assertions because it compiles them down, and then at compile time it passes the static asserts, and then at runtime it runs these assertions each one 3 times. So this actually satisfies the criteria that I was looking for, where I write the test only once. That's really nice. So let's take my tests that I've been testing so far. This time I have static require and static check. So one of them is fatal, one of them is non-fatal. I mean, at compile time, is there a difference? Not really, but still at runtime there is going to be a difference. I'm going to factor this out like I've been doing before. Again, don't repeat yourself, the dry principle. And I'm just going to run my assert parse success macro, and that passes. I don't need to show you that passes. It passes. But what about when it fails? This is the message that it tells me. It says static assert failed, iso date : parse of bad.hasValue. And it does the optional thing again. But at this time, actually, it tells me what static assert failed, which is nice that I don't have to go in and do that myself. It has that automatically. I'm going to take a break from catch2, actually. Because, yeah, the static assert message is good, but I'm going to take a break from catch2, go to the other catch2 API frameworks, and I'll come back to catch2 afterwards. So with doctest, actually, there is no static require and static check. There is only static assert. So when I try to do this, I'm only using static assert. When I try to run my tests, I'm just giving it an X. Sorry. It's a great library. There's a really good talk on it from CppCon 2016, 17. It's really good. Not for these purposes. Now let's look at snitch. Snitch has something called const eval require. So it doesn't have static require, but it has const eval require. It also has const expr require. What's the difference? It's the same as the difference between the const expr function and a const eval function. So a const eval function can only be run at compile time. A const expr function can be run at compile time and at runtime. And then something without any annotation can only be run at runtime. Snitch takes this exact same approach, and I think it's really cool. So these are only checked at compile time. And of course, that passes. But I want to check things at compile time and runtime, so I use const expr require and const expr check. And of course, there is also const eval check, but I didn't show that one. So again, I have these test cases, but I want to factor it out because I don't want to repeat myself. So I have my assert parse success macro. I'm going to call that, and everything passes. Something interesting you might notice is that there are 5 assertions. We'll get to that in a second. Why are there 5? So what if I try to fail the second check? Not the first check, because I've been doing the whole time, but I want to fail the second check. I want to make sure that the value that's expected, or the result that's expected, is not actually correct. So this is what it gives me. This is a runtime failure. I'll take a sip of water for a second. I'll let you take this in. This is a runtime failure. But it's a compile time test case failure. So if you notice, the same test is failing, or the same test case is failing twice, once at compile time, once at runtime. But the runtime failure is reported, the compile time failure is reported at runtime. So I was working on my talk, and I was getting through all these different frameworks, and I got to snitch, and I had to stop. And I had to rethink my entire assumptions of how compile time testing is supposed to work. Because before this, I thought, well, yeah, you have a test case that is failing at compile time, well, and therefore you have to fail the compile, right? Those two things are together. They're not. You don't have to do that. And snitch doesn't do that. And I think that's really cool. OK, now let's try failing the first test case. So this time, actually, I do get a compile error. But the reason that I get a compile error is for the same thing we were talking about a few minutes ago. It's trying to dereference a disengaged optional, which is UB, which is a compile failure. So what I need to do in my macro is put the constexpr check under an if constexpr, and then if that didn't pass, I'll just do a regular check. Yeah. I need to check the condition twice. So my constexpr require has the condition, but then I also need the condition inside of an if constexpr. Yeah, it's not ergonomic. It's not the fault of the library. It's the fault of the way I've decided to test this. So this is a problem that I need to solve. It still gives me a compile error. OK. I need to put an extra context around it. I need to put, I put a template lambda around this thing. And now actually it works. And by works, I mean it reports the compile time failure, but it reports the compile time failure at runtime. And what's interesting is, because it's a constexpr require and not a constexpr check, it only reports the compile time failure. But if it was a check, it would report the runtime failure too, right? Because it's reporting everything at runtime. So the first fatal error that it sees, it fails the entire test. But if it was a check, it would show both compile time and runtime. And so that's why before it said 5 assertions. Now, I can't actually understand why it's 5. I thought it would be 4. But regardless, it's not 2, and that's what's important. It's checking all the things at compile time and at runtime. I can do the same for catch 2. I can make this exact same sort of macro where I have the thing guarded under if constexpr, and then I have the same context with the lambda, and then I immediately invoke it with, doesn't matter, just a default constructed int. And this gives me a compile failure. And it gives me a helpful compile failure, right? It tells me that this test case has failed. But I've seen the light at this point, right? Like I don't even want compile failures anymore. So I'm sorry, I have to give this an X, even though like it does the kind of things that I want, but like it doesn't go the extra distance. Because the extra distance of what I want is the customized error messages. How do you get a customized error message if I'm failing the compile? I will talk about that later, but in Stitch, you don't even have to care, because here it's not failing the compile, it's just failing the run. And so what I can do is I can stick an info macro in, right? Because it's reporting at runtime, and the info macro is a runtime thing, and std format's a runtime thing. But who cares? It's a runtime report. And so this time, if I try to fail this, if I try to run this test case that fails, it actually gives me something that's nice, and it's at compile time. Yes?
So if it produces different results at compile time versus runtime, will the compile time failure show the runtime values in the error message?
No, it won't. Actually, it won't. I don't show that. That's a good point. I should have shown that. No, it won't do that because it captures what the value is, and it reports the correct value. So yeah, no, that is a good point though, because yeah, if the compile time and the runtime are different, they shouldn't be different, but that bug still exists. So yeah, we have to be aware of it. Yeah, so again, it's reporting this at compile time. And again, if I have my February 29th example that I need to come back to at this point, I can actually see what's wrong with this. It failed the compile because February 29th is not valid here. But I can see exactly why it's valid with a runtime formatted string. That's awesome. I'm giving it a check. My first check at compile time. Yes?
So this is reporting this at compile time, or it's reporting the compile time results at runtime?
It's reporting the compile time result at runtime. I may have misspoken at some point because it's a lot of words. But yes, it is detecting that it has failed at compile time. It's keeping that result, and then it's reporting it at runtime. Yeah. Which I think is really cool. Yes?
So does it store it in, I mean, is it running the tests immediately after compilation, or is it storing it in a file and just no?
Yeah, I mean, it's stored in the data in the same way that like a const_expr variable is stored in the binary.
That's
right?
exactly what it's doing, right?
Yeah, that is
So
what it is.
you do the Boolean evaluation of whatever requirement you want. That gets stored to a const_expr bool.
Yeah.
And then at runtime, that bool is checked with the test framework's assertion, right?
Yeah, exactly. Yeah, and before I wrote this talk, I didn't even think of that being a possibility. I was a little bit more narrow focused than I should have been. Let's get to the last one with UT. UT also actually does a similar thing to snitch, but it wasn't as mind-blowing at that point because I had already done snitch. So the way that you do it is you use the variable template constant, which is just a bool. So you pass in a bool and it returns itself. But the important thing is that it's inside angle brackets, meaning it evaluates at compile time. So you end up with expect a compile time thing. So that's what it does here. So I'm just checking that parser of isodate, like that's a concept. I'm putting that into that constant. Coincidentally, it is a name collision with my library, but that doesn't matter. And then, yeah, it's just reporting in the expected. And it reports just like this, everything passed. But it is only 3 asserts. It's not running both at compile time and at runtime. If I want to make it run at both compile time and runtime, I need to introduce a macro. I know it's a macro-free testing library, but I don't know any other way to make something run both at compile time and at runtime than to introduce a macro. So I'm sorry, I'm doing it. And it's doing exactly the same thing. It's checking whether the parse succeeds both at compile time and at runtime, and then it's checking whether the parse gives the right value both at compile time and at runtime. I'm doing a fatal error message for the runtime, but not for the compile time. It doesn't really matter. So here, I'm checking that everything succeeds and everything does succeed. I'm going to do the same thing I did with snitch, where I checked the second condition first, and it reports that a bunch of things failed. The problem is it doesn't actually tell me what failed because it's not macros. Again, it can't stringify things. But I can just give it a message if I want to. Well, we'll get to that in a second. First, I'm going to show off what happens when I fail the first test case. It actually gives me a compile error, and that's for that exact same reason, dereferencing the disengaged optional. So what I need to do is stick it inside an if const_expr. In this case, I don't actually need an extra lambda around it, but I do need to stick it inside of an if const_expr, and then everything works. And by works, I mean the test failed at runtime. Great. If I want a custom error message, I'm going to add more macros again. I'm sorry. So I have expect compile time and runtime failure. I'm going to pass in the message only once, because again, I want to write it only once, but I need to stream it on twice. So that's why I'm writing this macro. And similarly, I'll write an expect compile time and runtime non-fatal. This one doesn't take a message. If I was writing this in real production code, obviously I would make this more robust. But in this case, I want a message for the first one, and I don't care for the second one right now. And then all I need to do is call these macros from my main macro, assert parse success. And then when I do that, it ends up giving me this, which is exactly the message that I was looking for. Yeah, so it's the message that I was looking for. The difference between UT and snitch is that snitch actually tells me whether the failure is coming from compile time or runtime. And I find that to be a very valuable feature. So I am giving UT a check mark, but I am going to continue the parameterized stuff with snitch. So I'll get to parameterized compile time testing with snitch. I'll start with a concept. It's going to be called can sequence. And it's just whether or not the left-hand side and the right-hand side can be right-shifted together, basically. And then I'll create a function. It'll be the sequence tester. It's going to take in a pair of parsers. And it's going to check whether the value type of the left and the value type of the right are the same. If they are the same, then it should be sequenceable, because that's the limitation in my library. If they're not the same, it should not be sequenceable. And I print out this nice thing in the info macro because it's failing the compile. it's reporting the compile time failure at runtime, so I can have this arbitrarily whatever string. It can be a std format inside of this info macro that's only at runtime. Who cares? It reports it properly. So that's nice. Now, if anyone's ever implemented anything with like variadic Cartesian product or anything, this might be familiar to you with all the ... dots. Previously, I've used ... dots to mean like etc., but in this case, this is literal C++. So it's just taking the Cartesian product of every possible pair of this type list. So then when I give it a type list, I have two parsers here that have a value type of char. Two of them have a value type of wide char. I make the list, and then I give it the list. Well, it should work. Great. And for example, this is what it might give me. Now, mine actually passes, but if it didn't pass, this is what it might give me. It might say that L right shift R did not compile. L is any of 1, 2, 3. R is any of 4, 5, 6. And I take a look at this and I go, oh, well, those should have the same value type. And now I actually have something concrete where I'm able to reason about what's going on and not just say L right shift R didn't compile, but I might have 100 of them. Like, that's not helpful. So that's the compile time testing and runtime testing with all of these different frameworks. I like Snitch the most out of all of these. I think it gives me most of what I'm looking for. But I did say that I've been working on some testing before I found out about Snitch, and I'm going to show off my solution right now. I did have some prior assumptions, as I've mentioned already. I thought that a compile time test failure must fail to compile, which like seems obvious in hindsight, but it really blew my mind when I was working through this talk, and I had to rethink all of my assumptions and be like, where am I going with this? Am I going to be able to give this talk in the end? Well, I'm here now. But and similarly, because I thought a compile time test failure must fail to compile, I thought the error messages must be in a static assert, which makes sense. That's how you report a compile time failure. So working with these assumptions, here's from the standard. This is about static asserts. Notice that it says string literal. So a static assert message must be a string literal in C++20. That's an allusion to something I'm going to talk about later. So my mini testing library, it's based around this assertion macro that takes a condition in the message. It's static asserts in all caps because the static assertion can be disabled. So it can either be an actual static assert or it can be nothing, depending on how you configure it. And then there's also this function that's check condition. All it does really is pass the condition right back to you. But the problem is compilers might actually complain if you give it a condition that's evaluated or that's able to be evaluated at runtime, but you give it in a regular if. So I have to do it this way. And then I'm going to add an error for this message. The add error, of course, takes in a std source location, so it's able to detect all these different things. Now, this isn't a very robust testing framework, but it does work for my library at this time. The way that I create a test is by first declaring a fixture in the file. This fixture is going to be called any_of, and then I declare a test that's in the any_of fixture that's called parse single a. So I have my parser alias, and I'm going to check to make sure that that alias satisfies the concept. And if it doesn't, I'm giving it as descriptive of a message as I possibly can. And then I'm going to do the same for parsing. So if I try to parse AB and that doesn't work, then I'm going to give a descriptive message, the same about the expected result and the same about the remainder. I just want to give as descriptive messages as I possibly can. Next, I'm going to check something that is supposed to fail. So in this case, it's supposed to fail with BA because it's a parser that parses a singular A. And then also, the remainder is supposed to be still BA because it didn't parse anything. It didn't consume anything, so you still have whatever is left. And again, the descriptive error messages, I like being as descriptive as possible because I want to solve my bugs as fast as possible. So this passes, and this is a runtime pass. Now, if it was a failure, it would be a compile time failure. But I'm going to take this. I'm going to actually show what happens when there is a failure, and it fails at compile time. And it says this descriptive message. Any of a : parse of capital A, B does not give a valid result. To me, that's helpful. Like, this tells me exactly what's going on because it's any of lowercase a. Of course, it doesn't give a valid result. But it's just nice to see it because I might have written something wrong. So this is what it displays at runtime. If I disable the compile time assertions, this also works. So they display exactly the same thing. It's just you can display at runtime or at compile time if you feel like it. But the problem is it's very infeasible to write all of these things. I could just make a mistake at any time. I'll give you all an exercise right now. I want you to blink on the count of 3. OK. 1, 2, 3, blink. What changed?
Capital A.
Yeah, capital A. But you only see it because you didn't blink. So, oh, perfect. Okay, great. Okay, so then you see it. I probably wouldn't see it. And the problem is, if I'm repeating myself so many times and I need to copy and paste and I might make copy-paste errors, it's prone to error. I've been talking about this the whole time. Don't repeat yourself, the dry principle. So I'm going to not repeat myself. I'm going to show my assert parse success macro with something that's a little closer to what I have it in my framework, which is that first, I assert that the parser is actually a parser. I assert that the parse succeeds. I assert that the result is what I'm expecting. I assert that the remainder is also what I'm expecting the remainder to be. And at each of these steps, I give it a custom error message. And it's nice that I'm able to give it a custom error message at compile time. I can only do that because I'm concatenating string literals together, because it's a static assert. So that's the only way to do that. But at least you're able to get some nice things. So then if I try to give it something that succeeds, well, this is what it gives me, but that's not interesting. I'll try to fail the second condition of my for, which is where the parse does not succeed, and it tells me this. I didn't hard code that error message. It stringifies it stringifies the inputs to the macro, and it gives me an error message that I'm looking for, which I find to be very helpful when I'm trying to debug things. Now I'll fail the next condition, and it tells me something different, that the result is not what I'm expecting. And then lastly, the remainder, it's the same story. I just want as descriptive error messages as possible. That's the entire motivation for this talk. I just want descriptive error messages. Okay, I have the same test case as before that I've been using the whole time with the ISO date. This time I'm calling it P, and I'm asserting that assert parse success of P with today's date, May 2nd. And it works. But what if I give it today's date of May 2nd, but I'm expecting that to be equal to January 1st? For some reason, because I wasn't reading or because I don't know how calendars work. It tells me that the static assert failed, and it tells me exactly what failed. P : parse of this string does not equal to the tuple of those things, and I look at it and it's obvious. But it's only obvious, or I guess in this case it's obvious always, but, or no, sorry, it's not. It's only obvious because I know what P is. If I don't know what P is, it's not obvious. In this case, I constructed P explicitly in this test, so this should be easy to debug. What about in the parameterized case? What if I'm looping over a big list of parsers? How do I know? So the problem is I want to check whether the value type of L and the value type of R are the same. And if they are the same, then I want to assert that we can sequence them together. But how do I know if something went wrong? Where do I pretty print L and R? And the answer is that you can't. Not at compile time, at least. Sorry, not as a string literal, at least, I should say. So you end up getting this static assert failure. L right shift R compiled, but it should not. And I'm like, great, thank you. I have 100 parsers, and I'm doing the Cartesian product of those 100 parsers, and one of them failed? Like, where do I even start? Like, I could bisect the whole thing. It's annoying. I would like to actually get some custom error messages in the parameterized case, which was something that I've been working on. You just need more macros. So what I'm going to do is I'll define this all samples, and it's going to be any samples that I want. So in this case, like in my library, for example, I have like 100 or 150 different sample parsers. And so here I have any of one, any of two, I have a bunch of any ofs, I have a bunch of all ofs, I have a bunch of every type of parser. And I have this macro called assert all samples to that takes a binary asserter. Inside of itself, it just uses the all samples because you're just always using all samples. And it uses something from Boost preprocessor that does a for each Cartesian product, which is nice that these facilities exist. I mean, it's not nice that I have to do it, but the fact that these exist, Boost preprocessor, it's complete magic. So what I need to do instead is my asserter needs to be a macro. So now inside the macro, I'm able to check if the value type of L and R are the same. If they are, I'm going to assert that we can sequence L and R together. And I actually have a custom error message this time. And the same in the else case. I think that's great. So this will actually give me something that's valuable. I'm going to have only 4 samples in my all samples because, slideware. And then I'll assert that all samples to, the binary, with sequence operator asserter. And what does it give me? It should pass, but it fails. And it fails saying, like if you notice, any of ABC and any of ABC, like compiled, but it should not. So wait, my test failed saying that a parser was able to be sequenced with itself, but that shouldn't happen. Why is that? Well, it's because these asserts are effectively, one of them's assert true, the other one's assert false. and it's in a non-dependent context. Like these aren't dependent on the if const expr. So I need to do something. I need to surround it in a lambda. And now that I've surrounded it in a lambda, now everything works and everything's just fine. So that's what I've been doing to test my stuff. I'm going to summarize my framework. You declare a fixture with fixture of name, and you declare a test with both the fixture name and the test name. These could be strings of anything, not just valid identifiers. You assert with a condition and a message. It uses both static assert and runtime assert. I want to make sure that you can test something both at compile time and at runtime. That was one of my criteria. Also, error messages must all be string literals because I'm using static assert. If you want to loop over a list of parsers, I have a unary and a binary version of these things. And the result is that I get custom error messages that are, as pretty as I want them to be, and they are static assert error messages. So as much of a hack as this feels, it has actually really helped me in my development process before I understood that I could just do it the snitch way, and it would probably make things easier. But if I wanted to continue doing things my own way, here's some upcoming C++ features that might help me to do that. I'll take a sip of water before I get into that. I'm sure some of you can guess what it's about to be.
C++26 context for strings. And
Wait.
assert.
Sorry, what's the one you're saying?
Formatting strings.
OK, I'll get there. First, I'll talk about static assert false. So this is a paper by Barry Revson. It was a DR in, oh, my mouse moved. It's a DR in C++23. And what that means in the general case, OK, here's an example. Let's say I have a variant of int and string, and then I have a visitor that is supposed to visit this variant. I have a case for int, I have a case for string, and then I have a case for else. And this is static assert with a dependent false. And the reason I do that personally, I like this pattern, because if I add something to my variant, I want to fail to compile until I properly handle it in all the places that I need to handle it. And this is the syntax that I like. Yes, I know you can do it in different ways, whatever. But I like this syntax. It's the nicest one to me, but I can't do it unless I have always false of v. I can't just do static assert false. But after this paper in C++23, no one cares about that top thing. You don't even need always false v. And now you have static assert false. This actually works now. And it's also nice and yes.
I mean, always false v takes a type template parameter, and sometimes you have a NTTP that you want to assert, so you need more of them, right?
That is a good point. Yeah, because you need all the possible combinations of all the infinite, countable combinations of, you take an auto, you take a template parameter that has a variadic pack of types and a variadic pack of whatever. You don't want to do that, right?
Yeah, I don't do all that, but
no.
NTTP
No, but if you wanted to.
What we really need is higher kinded templates.
I'm sorry?
What we really need is higher kinded templates.
Yes, we need universal template parameters, but that's not what my talk is about. So yeah, static assert false is going to be really useful. Also for my use case, like in this case, in the sequence operator, asserter, sorry. Well now, one of these is assert true and the other one's assert false. And that's always the case because they are opposites of each other. But if this is in a non-dependent context, then one of them will be static assert true and the other one static assert false. So it fails the compile. I need to put that extra lambda around it. In C++23, I won't have to do that. And that'll be really nice. So I'm looking forward to that. Something else I'm looking forward to even more, and both of you said it, and you knew where I was going with this, user-generated static assert messages. I am unbelievably excited for this one. And this is in C++26, which is too bad. But still, this is a paper by Corentin Jabot. It is actually a really good read and very exciting. I will summarize it for you, though. So it expands what can be used as a static assert message. And the way that it does that, as far as I've read in the paper, is that your message either needs to be a string literal, as it was before, or it needs to have a dot size such that that's convertible to std size t, and it needs to have a dot data such that it's convertible to const char star, or char const star if you like it that way. And this is nice because it works for std string, it works for std string view, it also works for std array of char, which is kind of cool. It works for a lot of different things, and now you'll actually be able to have static assert messages that are completely customizable without being a string literal. That's nice. So it's accepted into C++26. Yes, I am excited for that. So I'm going to update my library in a few years. And the way I'm going to update it, hopefully, I'm actually able to call my pretty function. And I'm able to take the pretty version of my parsers, and I can store them as string views. These are I'm not sure if they're actually string views or if they're string view-ish, but they are are basically string views. And then again, I'm able to go in, I'm able to check whether the value type of the left side and the right side are the same. And if they are, I can use std format. Like I can just format this thing. This is going to be a static assert message, but my static assert message is going to be formatted at compile time. I love it. Like this is music to my ears or eyes. And the same in the else case as well. Some of you might actually notice something wrong with this though. Anyone notice anything wrong? I don't think std format's const expert.
I was looking that up because I wasn't.
Yeah, right, exactly. Is it const expert? Did you look it up? Because I can't remember if that's been proposed and accepted or if it hasn't yet.
According to CPP reference, it is not const expert in any current version.
Right. So I mean, what I'm showing here is a lie, and I'm sorry. Instead, I'll just use string concatenation, and that is const expert.
Or you could the format library.
I could use format lib. Yeah, actually, that's a good point. Yeah. Okay. So instead of std format, I could use format lib, which obviously has a lot wider support than the standard.
The one's not in standard, but always better than the one.
Yeah, that's how it goes. But I mean, I don't even have to do that. I can just use the standard, right? Like, especially in this case, it's a pretty simple string anyway. I don't need anything that complex. I'm just, inserting string views that I've already calculated. So I can just do string concatenation, and that is const expert already. And that's cool. Like, I can do this at compile time. So, can sequence L and R fails, but it shouldn't. And so it actually says, L right shift R did not compile, and here are the two parsers. Awesome. And at the lowest level, I'll be able to see in that message, at compile time, in a static assert, I'll be able to see in the message, oh, well, one of them has a value type of this, and the other one has a value type of this. Well, of course, so what's going wrong here and whatever. No, I guess they have to have the same value type. Never mind. I'll be able to go investigate those parsers specifically. And then again, in the else case, I'll be able to do exactly the same thing. OK. So in conclusion, yes?
Can I ask, do you know, does anyone in the room know if that static string protocol also applies to delete should have a reason?
I actually was talking about that with, was I talking about that with you a few days ago? Oh, I was the one who asked that in Jeff's talk. Yeah, exactly. I don't know. I haven't looked into that yet. I was trying to read the paper, but I've also been preparing for this. So, yeah, I don't know. And that is a good point. I think the equals delete should have a reason paper that was accepted into C++26. I hope that also accepts like formatted strings and anything with a size and a data as opposed to just a string literal. Because it would be nice. It would be a nice alignment with the static assert message. And if not, I hope someone proposes it soon. So maybe I'll have to be, I don't know. So anyway, in conclusion, token is a parser combinator library that parses spans of anything. I need to test it at compile time, but compile time testing is very hard, especially having the custom error messages, as you've seen. I've made a whole talk out of it. So there are some test frameworks like Snitch and UT that actually do something very interesting, where the compile time test failures don't actually fail to compile. And that really blew my mind. I didn't realize that at first, so I've actually been going with the static asserts. But if you do want static assert test cases, it will be a lot better in C++26. So I have some key takeaways personally. Try out some new libraries. You might learn something. I know I really did from writing this talk, so it's been a great experience. Also, dive deep and reassess your assumptions. Just in general, I feel like that's a nice life lesson, because I had this very low-level assumption that turned out to be false, and like I've been putting myself through a struggle for like 2 years at this point. So it'll be better. I might rewrite some things, or maybe I have the sunk cost fallacy in it anyway. And then my last takeaway is actually JavaScript is really cool. And this seems completely unrelated, but this presentation is in Reveal.js, which I learned some JavaScript for this. I've never learned any JavaScript before. And if you haven't ever done any JavaScript or Reveal.js, even like small bits of JavaScript, it's cool. Anyway, that's my presentation. Thank you so much for attending. If anyone would like to contact me, here's my contact information, and I think I have some time for questions if there are any. Yes?
So earlier you said you were having trouble getting the error messages as a string literal. Did you consider funcsig or pretty function?
I don't know how that would help in my use case.
Because you can do the string literal concatenation with funcsig, I believe.
Yeah, but I don't think I want the value of funcsig. Like I don't think there's anywhere where that's useful for me.
It would pretty print the types and the template parameter.
Template parameters, but
Can you do that, really?
Yes.
That's amazing. I would like to talk to some of you later about that.
Signature is
I mean, it gives you extra ugly cruft, but
Sorry, what was that?
it gives you extra ugly cruft around it, but it does include the information you want.
Sure, but it does the thing that I want. That's really cool. Okay. I'll have to look into that.
ugly, but
Great. Well then, yeah, right. So I guess you can take funcsig and you can take the parts that you want. And is that something like that?
something
Yeah.
like that.
But can you do that as a string literal? Like, how do you break off parts of a string
Well,
literal?
funcsig is the string literal.
Right. But if I only want like
I
a
don't know if
portion
you
of
can-
that,
It has
Yeah.
to be a parser.
but you can't pass it through a parser. Right. No, listen, I would love to. I really would love to. But then you can't get out a string literal on the other side. So yeah. Yes.
So maybe this is obvious to others, but why would you want to not fail your build at compile time if you've got a failure, if you have a compile time unit test failure?
In my case, it's just so we can get better error messages.
I
That's
also
why.
wanna see how
But
much-
is there a better reason?
Yeah.
You can get all the failures at once in
Yeah.
a run, rather than just
Ah.
getting one at a time every time you get a compile.
and that can give you a better hint as to what the problem is.
Okay. Well, I never had that many failures all at once because I would sort of write a test and fix the failure as I was writing the test. So I didn't have to deal with that sort of thing. But yeah, I mean, in a production case, I'm sure it would be a lot more helpful to have it at runtime.
Multiple failures can happen when you're refactoring.
True.
Yeah.
That's also true. Yes.
Just to add on to that, another reason is because you would want to have it in a debugger, and you can't like have a. There's no compile time debugger, so having it run at runtime
True.
and putting it in the debugger is useful.
Well, but still, the test is still running at compile time, though. So you can't debug the test.
But if you run it at compile time and runtime,
Yeah, then you can
don't
debug the
have
runtime
compile
one. Yeah.
one.
Yeah, definitely.
Both give the same result.
Yes, assuming that you
If,
don't have
assuming they give the
MSPC
same
bugs,
result,
yeah.
then yes, you can debug it at compile time as well. That's true.
And then the other thing is that static assert false was forwarded as a DR, so it might be usable in earlier C++ versions as well.
It was forwarded as a DR into C++23 after C++23 was already feature frozen. So yes, like it is in sort of previous versions, but the previous is 23. So yeah, but at least it's not 26. Yes.
I was going to ask if the type or the template type result for is that fascination?
What do you mean?
Like, does it cause substitution failure rather than a hard error if you pass something that is not compatible with the value
Yes,
type?
I think it does. Now that you mention it, I don't have any tests where I try calling result for where it doesn't work. So that's something to add. Thank you. And then I think, Ben, you were going to say something?
I was going to ask if you have any thoughts on property-based testing, or since you're writing your own framework, do you have any plans to add any of that?
I will confess my ignorance and say I don't know what that means.
Well, in brief, instead of writing example test cases,
Mhm.
you write invariant properties of your code. The canonical one would be if you're
Okay.
testing reverse, then reverse of reverse gets you back to
Right.
original. Right. And that's an invariant of the algorithm. And then the framework generates inputs, trying to find ones that fail. When it finds one that fails, it tries to shrink it to the least possible example and then report that.
I will have to look into that.
It's
That
really
sounds
cool.
yeah, that sounds really cool. I like that. I will look into that.
Take a look at rapid check.
Rapid check.
Is,
Okay.
C++, and then quick check and
Got it.
hypothesis.
Cool. I will do that. I love learning things during my own.
We're trying to nerd snipe you because we want this.
No, you should. I mean, listen, I've been fully nerd sniped by Ben's talk for years, so you can nerd snipe me again. Yeah.
The key thing about rapid check, though, is still, I think the real source code was last updated 7 years ago.
Yeah.
So then,
It works, but it's fallow. Yeah.
That's okay. Yes.
To this point, Google Fuzz Test exists, plugs in with the rest of Google Test, and like does all of this as well. You can do property-based testing with normal Google Test matchers and vectors.
Very cool.
What was that?
That's good to know.
Does minimization?
Yeah.
Does it what?
Do minimization?
Yeah, it runs on top of. I think you get to choose your fuzzer framework, but typically like the fuzzer.
Yeah, it does do minimization, though, right? It does.
Well, I mean, it runs on top of a fuzzer, and the fuzzer does it. Yeah, I think the fuzzer will do some sort of minimization.
Okay. We have that.
Okay. You should try that.
Cool. That's good to know. And also, I mean, I just love like rewriting my own things too. So writing a test framework was a lot of fun as well. It's a valuable experience. Okay. So if there are no more questions, I'll say thank you again for coming.